What's up, guys? It's Kayla.
And Jim.
And welcome back to another Meteorology Monday. What are we discussing today?
What we are discussing today is something that has been requested.
It has.
By some of the folks who watch our channel. And that is another case study.
Another case study.
And this one specifically will be the Jarrell, Texas tornado of May 1997.
There we go. Thank you for suggesting this video. And before we get started... No, we're switching it up this week. You do it.
Don't forget to subscribe by clicking on the subscribe button below. And don't forget to give us a thumbs up.
Hey! An extra thumbs up for Dad for doing that part.
She usually does it. My mind goes on autopilot, so I'm just... So now we're gonna dive in. What do you think was probably the most unusual thing about this setup?
The fact that the kind of atmosphere that this tornado formed in should not have formed a tornado. In fact, it shouldn't have even formed hail. And this thing put down 2 F3s, an F4, and an F5 all within like an hour of each other.
And again, we don't have all the records, all the imagery and stuff like that because it was 1997. Yeah. Some of the archives don't go back that far.
Let's explain that. I spent a good 2 hours trying to get NWS to pull up the archives for 1997. And they're like, nope, we started in the 2000s. Good luck. Gonna have to find a chalk map somewhere.
I think we had GOES 8 back then.
It was GOES 8.
We're at GOES, what, 16, 17 now?
16 and
so
17.
We're talking a long time ago, older technology, you know, each cloud pixel I think was what, like this back in the day, and it covered, I think it was either a 12 kilometer by 12 kilometer box. It might have gotten to 4 kilometer by 4 kilometer, but back in 97, I mean, that was the amount of information in one image, and just sending that across your network and then trying to repeat that every 15 minutes, it chewed up a lot of bandwidth. So
yeah, bad
you
quality.
know, now it looks like it almost like you're taking a camera and snapping a picture and going, here you go, whereas back then it wasn't quite, it had a lot more you know, a lot more grainy, and but it was still good for the technology at the time. They did make quite a bit of advancements. But again, trying to go back and find that, it's hard to get that. Anyways, getting to this, it was really interesting in that the environment definitely was not set up for there to be the magnitude and the strength of tornadoes that occurred that day. The Weather Service, SPC, had an idea, okay, you know, looks like there's going to be some potential here, but to that degree, it just didn't set up the classic way. So we're going to dive into a little bit of those details today.
There we go.
In this video.
So first, I guess we should get into where in the world is Jarrell, Texas?
Jarrell, Texas. So that is in the, if you look at the state of Texas, more on the southeast side toward Austin. So most people know Dallas-Fort Worth, so just go south from there. They know the Mexican border, go north of there, and somewhere's where the two meet. That's roughly where Jarrell, Texas is, south of Waco.
In that area.
Yeah. So we're going to look at the first image is going to be a national view of the United States, and you'll see the fronts and low pressure areas and all the station plots that are reporting weather parameters for that particular hour. And then we're going to zoom in to Texas and see the area of interest. And you'll see that there is low pressure right there on the Oklahoma-Arkansas border at this time. Our stationary front that kind of goes along the Arkansas-Tennessee border, and a cold front that drags down through southeast Oklahoma into central Texas. So out ahead of that, you've got a lot of very warm, very moist air. So those numbers there on the left side, you'll see circles, okay, on the station plot. And as you're looking at it, on the left side, the top part here, that's the temperature. The bottom part is the dew point, and the closer those numbers are together, the higher the relative humidity. So one of the thresholds is when you have a dew point, that bottom number over here, when that is at or above 70, it is oppressive humidity. So usually as meteorologists, we get really excited when we start seeing dew points at 65, 70 degrees out ahead of a cold front, and that lets us know one factor in the instability. And no, these are station plots at the surface. So this is at the ground, you're getting high moisture readings. So right there, okay, we're starting to set things up. What is not labeled on here is the dry line that had formed earlier in the day, and that is just a little bit east of where that cold front is. So as you're looking at, here's the cold front.
East.
It's going to be a little bit further east, not down where the Gulf of Mexico is, but closer to it. And eventually, this cold front starts to meet up with where this dry line is. And so it's almost like a zipper effect. As the cold front is kind of coming through,
Meshed together.
it's creating that uplift and kind of squeezing that
all the
moisture
air in between
and air
stuff goes,
and starting to create this energy and this atmosphere. And so as they're meeting in the northern part, and kind of like a zipper effect going down as they're meeting going toward the southwest, these parameters come together, the atmosphere is starting to get primed, and also there was a mesoscale convective system that had developed off to the northeast and was making its way further south. It kicked off what they termed a gravity wave. We won't get into all those details, but it created the additional energy aloft that as this was coming through and as the zippering effect was occurring, all the dynamics started coming into place. This was setting up to be a very interesting afternoon for our National Weather Service offices in that area and for SPC.
So next we're going to show a radar image of what it looks like when a dry line and a cold front come together. This is not the Jarrell, Texas storm, but it's an example of a similar thing happening. So let's take a look at that. See, we have a dry line, we have a cold front, and as they come together, you just get this huge amount of like instability. You get a lot of shear along that line, and it blows up into this huge line of storms.
That's right. And it runs a little bit fast in the animation, but if you notice where the dry line and the cold front meet, you'll see that that's where the storms develop and explode first. And then as it continues to merge, you'll see more storms firing in that zipper effect we were talking about earlier. All right, so as things are setting up and coming together, Storm Prediction Center actually issued a moderate risk earlier that day, and it covered the area of where the cold front and the dry line were going to meet up, along with the MCS that was moving down from northeast to southwest over that same area. One of the other things that was observed with this event was the lack of a low-level jet. So something down 5,000 feet above sea level or lower than that. Usually you have winds come out of the southwest here in the US, or could be out of the southeast too, especially along the Gulf of Mexico, especially in this region, southeast would be good. So you've got that speed and the moisture transport in the lower layers to add to the instability, but that was not part of the mix.
It was not.
Here. In fact, if you look at the one image here at the 850 millibar level, which is again roughly about 5,000 feet, you notice that there isn't much of a strong, when you've got those lines of equal heights compressed together, it shows more wind speed. And you don't have them really tightly compressed over the Austin area of Texas.
It's just there. There's not really anything to indicate a jet and that fast air movement and the shear that brings. So it's a very low shear environment overall in the atmosphere over central Texas.
That's right. So what we've got right now is a lot of moisture sitting in the lower layers.
Yep.
You've got some overturning and atmospheric dynamics from the MCS, from the mid layers and higher that have moved through. You've got a cold front and you've got a dry line that are coming together, pressing and making a line of convergence. And since the air can't go down, since you're at the surface, the only place it can go is up. So there's your uplift, and these things are starting to come together.
We did, however, we had a lot of CAPE in the atmosphere, about 7,500 joules per kilogram of CAPE, which, to put in perspective, 4,000 is huge. Like if you have 4,000, it's like, all right, something's gonna happen. And there was 7,500 on this day. Wasn't a lot of shear, but there was high CAPE, so that's what we call a high CAPE, low shear scenario.
That's right. And what is CAPE?
CAPE is convective available potential energy. So it has to do with your moistures and your heat and the amount of potential energy that the atmosphere has because of it.
That's right. And usually higher CAPE indicates the strength of an updraft within a storm. So it basically, the more CAPE you have, the more possibility that there is that a parcel layer at the surface will be driven upward at a higher rate of speed.
Yep, and then you need that shear to take that going up and turn it into spinning motion. So in this scenario, we have a lot of uprising, but we don't have a lot of spinning air.
And going back to what Kayla said earlier, 4,000 joules, and the unit of joules per kilogram is what they measure CAPE with. The measure of 4,000, that's the bar set that the Weather Service uses as extreme.
Yeah.
An extreme value, so anything from that point up. And so this is almost double that at one point, 7,500 joules per kilogram. So you're talking a lot of energy, atmospheric potential here of rising motion very quickly. And so that led as one component to rapid intensification of all these thunderstorms that just happen to blow up as these two, the front and the dry line, merge together. So it can be difficult when you're taking measurements that morning, surface sites, upper air observations using balloons and radiosondes, raywindsondes. You know, you get a static image of what's happening, but here's the real-time dynamic things that are happening as the cold fronts merge, as the MCS rolls over. We don't have the rapid update model cycles like we do now. We don't have the Doppler radars back then weren't updating as frequently. They didn't have the granularity to see the detail. They weren't dual pole. They were only looking at a scanning in a certain orientation.
And at one point the radar goes out.
At one point,
the radar just stopped. So at one point they're completely blind.
We're done. We're going home. Have a good one.
Back it in.
That's right. So, you know, satellite images only updated every so often. So you had a lot of these factors that we take for granted now because of the increase in technology, but back then you didn't have. So all these things, when they start happening in rapid succession, the forecasters here are now trying to keep up. And are seeing this happening, and they did a great job trying to do the warnings and letting the public know with the technology that they had. Unfortunately, there was still lives lost, and unfortunately there's going to be that potential anytime you have a rapidly developing situation. That potential is always there, no matter what your technology is. But so that's the setup.
Next, we have a satellite image that shows that same thing that we were looking at on the radar. This is actually from Jarrell, Texas. You can see the date on the bottom there. And here we have the cold front. You can kind of see it here. I'll point it out in the editing. You have your cold front here, and as we play the video, you can't really see the dry line, but as it merges, it does that zipper effect that Dad was talking about, and you see these storms just blow up. Look at that. It starts on the north end and goes to the south end of the cold front as they merge together. That was another very strange thing about this day. Normally you have the influence of a low-level jet and stuff pushing storms from the west or southwest to the east or northeast, and it goes from the west side of the state to the east side of the state. In this instance, since they merged top to bottom, you had storms from the north going southwest, which normally when you're out storm chasing, you always look to the west to be like, where are the storms at, you know? These storms were coming from behind you. Try imagining that for a second. You're looking in the wrong direction for storms. It just added to the whole craziness of the day.
The funny thing about this was when a typical storm blows up and you have the tornado forming in the southwest corner, let's say, that was actually, that southwest corner was the leading edge of the storm where the tornado was, instead of it being at the back end of the storm.
Going right off of that, here is the radar image of the storm at approximately 3:24 p.m. It hit at about 3:40 p.m.-ish, so this is just 10-15 minutes before. And there you go. It's not, I mean, you can see like the Lego bricks that was the radar. Fantastic quality, but something that's missing is the hook echo. Normally you have this really defined hook, and in this case, it just kind of looks like a blob.
That's right.
But that's an F-5 tornado right there.
Yeah, very rapidly intensifying at this point. This storm has been dropping tornadoes
Yeah.
on the way down toward
Yeah.
Jarrell. It's been dropping F3s, F4s. So I think I read that there was up to 4 or 5 tornadoes before it even hit Jarrell at this point from the same storm system. Here we are, the storms have been popping, dropping tornadoes, it's doing its zipper effect, and now the storm has made it southwestward toward Jarrell, Texas.
Yep.
And now it is starting to do its thing. What are some of the interesting highlights from this storm that actually happened?
As we've said before, it was an F-5 tornado, which, characteristic of the F scale compared to the EF scale, means that it was 260 plus miles per hour when it went through Jarrell. It was 3/4 of a mile wide, and it left a 7.6 mile long damage path. It went through a subdivision called the Double Creeks Estate subdivision and left it completely flattened. There were only 30 deaths that day from the storm system, and 27 of them were from that subdivision alone. And it was, up until that time, the first, and since that time, the only F4 or F5 tornado to ever go through that part of Central Texas.
Yeah. So Williamson and Travis County never reported a tornado that strong before in their recorded history, and hasn't been one since.
Nope. Not only was this a weird event to start out with, it was like a one-off F4, F5 tornado event also. Like, this just, it doesn't happen. And then you have an atmosphere that it shouldn't have happened in, and it happened anyways.
That's right. One other interesting fact about this tornado was that it had a forward moving speed of about 15 miles an hour. So with it being 3/4 of a mile wide, if you went through the middle part of that tornado, it could take up to about 3 minutes being in 260 mile an hour wind. It might not have been 260 the entire 3 minutes, but the point being is that you were in the intense core of that tornado for up to 3 minutes. And that is, as you've seen on some of our other Reacts videos, being in, I think we did a 10-second pause.
Yeah, for Greensburg, Kansas.
For the Greensburg, Kansas tornado, just to give, a small amount of time being in that, and that was just very small because it was actually much longer being in those winds. But I mean, that's crazy, being in an F5 or an EF5 for 3 minutes. I couldn't imagine. So some of the damage associated with an F5 was the trees being stripped of their bark and uprooted, well-built homes completely leveled and swept off the foundations. Even the plumbing was gone. The asphalt actually being torn up from the roads.
Yep. It took the roads with it.
Yep. There was cars that were lifted and carried a half mile away from their original location. So just crazy stuff.
Unimaginable damage. What is it? Inconceivable?
Inconceivable.
Inconceivable damage. That's what they call those kinds of tornadoes.
Yep. And one other thing to note, and that is that this wasn't the first time this happened in a high cape, low shear environment. There are other cases where this similar situation happened.
Yep.
Maybe not necessarily from a cold front and a dry line coming together, but in terms of a high cape, low shear environment where, okay, we're not expecting strong tornadoes. Strong tornadoes actually occurred. And there's Jordan, Iowa, back in 1976.
Yep.
There's Grand Island, Nebraska, 1980.
Which inspired the book Night of the Twisters, which inspired the movie Night of the Twisters, which we have a reaction video to. That'll pop up in one of these corners where a fridge gets completely yeeted through a window if you want to check that out after this one. And there was also Plainfield, Illinois.
That's right, 1990. So, it's not unusual, but it is not typical for your classic setup for strong tornadoes.
As always, we include footage of the actual event and the damage afterwards, so we're gonna put that in right now. have it, the Jarrell, Texas tornado of May 27th, 1997.
And we really appreciate you guys offering up suggestions for case studies.
Yes.
We really enjoy doing these, so keep them coming. We've got a list of them, more to go.
Very long list.
So, but keep them coming, and we hope you enjoy this one as well.
Yes.
And if you like what you saw, go ahead again, give us a thumbs up, and go ahead and click that subscribe button down below.
Until next time, I'm Kayla.
And I'm Jim.
Thanks for watching.
And may your storm systems zip in the right way.
Thanks for watching.
And may your storm systems, oh God, do it again, I started laughing.